Hi, welcome to another video. So this is how to program your analog device's AD9833. It's a low power programmable waveform generator. Could I get this little bugger to run? No, I couldn't. I even thinking the chip must be faulty. You can see there I bought another one from Farnell. Those little MikroC devices, about £7 something each plus the VAT. The people I got this off asked them for some help. They were useless. Didn't even give me the right pin configuration. So it's a programmable waveform generator, 3 lines SPISO, serial data, serial clock and chip select. Hopefully you're familiar with them, but writing just simple SPI code wouldn't work, not for days, and I'll show you why. So I've got that running on MikroElektronika's Fusion board. So you can program this with any microcontroller, but I'm obviously using the MikroElektronika's software. Got it on the Fusion 7 board with the Pic32 MX795, but you can use an 8-bit microcontroller as well. So if I put this scope lead in there, I've got some code and shown the scope on the screen, but it's a bit slow. So this is actually what the scope looks like. If I can reset the controller, now it's gone under screensaver. I've just got that shifting from 30 Hertz, and it just keeps on going to whatever it goes up to. I've not seen yet. If I can trigger it. Where's the trigger? Trigger source 1. If I start that again. Well, the example I'll show you is 400 Hertz, but this code starts at 30 and just keeps on running up. So it can't automatically ramp, you've got to program it. And you can get sine wave, square wave and triangle wave. And I'll show you the code. Let you watch that for a few seconds. So you can see we're up to 1.2 kilohertz now. And that started at 30 Hertz. That's a MikroElektronika board, and I do make a note on the video coming up. This crystal is 25 meg crystal. Right, so here's the 2 PDF sheets I'm using today. Analog devices, programmable waveform generator, AD9833. That's the 26 page one. There's other variants on the internet. Find the 26 page one, and this application note, AN1070, because down the bottom it's got a simple programming guide. We'll be writing the frequency we want to this 0 register, and it's 28 bits long, so that's where we're getting a 28 from. Carry on scrolling down, and then 5 simple steps. Here. You write these into your compiler, program it, and you're away. Or you're away when it works. Simple when you know how. And believe me, it's not that simple, because the timing on these devices is critical. And I'll show you why it took me days to get mine going. So let's work out this frequency first. So my board has got the onboard 25 megs crystal oscillator. So my board is the same as this example here. So make sure your board has got this 25 meg oscillator. If it hasn't, you need to work out your frequency out and then divide it by your oscillator frequency here. So if I pull up the Windows calculator, so yes, although I've used it recently on sort of TFTs and working out the clock frequency or scanning frequency of TFTs, I haven't used a scientific calculator for the 30-40 years. So for those of you who are like me, need to refresh your memory. So we want frequency out. So he's got 400 Hertz sine wave as his example. So change of view, standard, scientific. So 400 Hertz multiplied by 2 to the power of 28. So multiplied by 2 times 2 times 2 times 2 times 2, 28 times. So 2 to the power of 28. So multiplied by 2. Then you want this y over the x. So 2 to the power of, and see that symbol there? That's in your compiler. So you could actually get this equation, work it out in your compiler. So 400 times 2 to the power of 28 equals, forget this huge number, divided by your clock frequency of 25 million. So 3, 4, 5, 6, 25 megs equals, got 4294.9, so he's actually rounded it up, so 4295. So switch to programmer view. The decimal is still highlighted in blue, so make sure you're on decimal, not binary. You can see depending which one lights up blue. So we want decimal 4295. And that gives you a binary representation down there, decimal and hexadecimal up there, 10C7. So that's his example there, 10C7. So we're doing something right because we're getting the same results. So just up to the top right hand corner, control register. By default here he's got it 2100 hex, and he explains why. So we're writing the frequency in 2 consecutive writes, although that's, I don't know, confusing, ambiguous. It's not 2 consecutive writes, it is actually split with the chip select or frame select that I'll go through later. This is the frequency here. Now this is where it gets slightly confusing. So remember, we've got this 10C7, and that's the binary representation. But we've got to OR this with these bits here, dB15 and 14, that are already set to 0 and 1. Frequency register, he's got 0x50C7. Frequency register 0, least significant byte, or least significant bits, 14 of them. So pull up the calculator. We've got our frequency there, but that's 16 bits long, so we need to cut off 2 zeros. But make sure you're on binary here. dB15 and 14 are set to 0 and 1 respectively, so 0 doesn't do anything. Put a 1 there for bit 14. Then we've got 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So this frequency register 0 has got to start with a 1 there, followed by our frequency. And because it's only 400 Hertz, makes it easy. We've only got 1 register to deal with, not the second most significant byte. So we've got to OR this with this number down here. And this is 16 bits long, so knock off 2 zeros, which he's done so already over here. So we've got to keep this bit 14 as a 1. So 14, then knock off 2 zeros, we're left with this bit over here. So 14, 0, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. That's our 50C7. And then 4000 is the frequency register most significant byte, which isn't used because we're dealing with a low number. Next register, phase shift. is just by default 1 1 up here. So you can see bit 15 and 14 are 1 1. And then to exit the program, we just put a 1 there. Simple when you know how. Right, so in my code, I'll show you later, all I'm doing is incrementing this frequency, and when it fills up to here, not interfering with these 2 bits, I'm just incrementing these bits, and then when that fills up, I'm putting a 1 here, and then when that fills up again, I'm putting another 1. I'm shifting this 1 up here, and so this most significant byte starts filling up, and there's me pointing at the screen, but you're not going to see it because I've not got the camera on. So that's what my code is doing, just putting 1 there and then shifting it up. Right, turning to some code. So remember from the data sheet, this simple example, so 2100 50C7 4000 C1000 2000. And I thought, great, simple, 5 steps. So you've got to select the device with the chip select, which is also called frame select on the board, I believe. So chip select equals 0, and I've just defined a pin at the top, as we're going to show you. So mine's on lat D14. Now that's actually important. I'll tell you why in a minute. Initialize the MCU, everything's digital. SPI, so SPI initialize, or SPI 3, because I'm using one of the click sockets on the Fusion version 7 board. I've got the MX795 running at 80 megs, but the peripheral clock divider is divided by 8. I'll show you down here. If you're having trouble with your SPI, maybe your clock's running too fast and you've actually got to watch the baud rate or the clock time. So look, peripheral clock is system clock divided by 8. So system clock, which is 80 megs, divided by 8 gives you 10 megs. So I go cancel, and then I'm dividing that by a further 20. So I'll bring up the calculator. So 80, 1, 2, 3, 4, 5, 6, 80 megs divided by 8 equals 10 megs. Then divide that by 20. So divide by 20 equals 500 kilohertz, or 500,000 hertz. So 500 kilohertz, that's what my SPI clock is running at. If I didn't divide the peripheral clock by 8, I'd actually have 4 million here, and this analog device is actually capable of running with a clock speed of 4 megs. I think that's its upper limit. Anyway, we're not using the slave select. Sample the data in the middle of the clock. The clock idles low, idling high doesn't work, and then SPI active to idle. Forget these bits, come back to them in a minute. So I thought in a while one, I kept on writing it, kept on writing to the device. There's the example, so that's the start, that's the frequency least significant byte, most significant byte is empty, phase shift, and that's exit. And I've got some notes there. Look, 2020 gives you a square wave, 2002 gives you a triangle, 2000 gives you a sine wave. So if I can pull up the scope, did this once. I came down one morning, turned it on, and I had 400 hertz. The rest of the time, it was all just nonsense on the screen. If I pull up the scope until I get my camera out, I'll show you what I've got. So you think, simple, just write those commands. So what I was saying about the datasheet being a bit ambiguous, or how I construed something, this allows a complete word to be loaded into the frequency register in 2 consecutive writes. So going back to the here, so this low part of the frequency, remember it's 28 bits long, or can be up to 28 bits long. There's the low part, and then there's the high part. So that's 2 writes, but it's not consecutive because we're split with a chip select. We're turning it on here, then off, then on again, then off. So yes, we've got two writes and they follow one another. So you know, you could construe that as consecutive, but we've actually got to split it with a chip select every 16 bits. So look there, that's 16 bits, chip select 0, chip select 1, chip select 0, another 16 bits, chip select 1, and then just, so we've got 5 writes. Right, let me pull up the scope, show you this nonsense with this code, and it wasn't working. Right, this is my Keysight bench view. It's plugged into the scope at the moment, but because of the update is a bit slow, you're not seeing the noise on my screen. But so this is the default program you just seen, meant to be 400 Hertz sine wave, and look up here, 12.5 megs, and that's actually a lot of sort of random noise on the screen. If I get a screenshot, there we are. Let it update. That's the noise I've got on my screen at the moment. That is not my 400 Hertz sine wave, and that's what I had for a couple of days. I just couldn't get this bloody thing to work. What a bugger. Asked the supplier if they could help, but as it is their data sheet on their website, they had the pins all wrong. I mean, for example, there's a reference pin. They said I should go to ground. The reference pin on this sine wave generator is actually the reference oscillator, so sort of 25 megs out, and you ground that. All you're doing is loading up the crystal. So that's what I had on the scope. Now, while I've got the scope, I'll show you what that SPI is doing. So I'll move my leads and show you the clock and the chip select. So if I go to this data sheet, find the right bit. So although it's simple to program once you know how, so look at this system clock. There's our system clock. There's our frame select or chip select. So it's active low, so we have to pull it down just like a TFT, run our 16 clocks, 16 bits of data, and then turn the chip select off again, and you see our data down there. So that's got to coincide with the data, and then obviously synchronize with the clock somehow. Right, I apologize in advance if this microphone started clicking. I'm not sure if it's this oscillator running in the background or what. Anyway, this is the system. This is my SPI clock. I've just decided to shift. I have to wait for this screen to update. There's my 5 writes, and this is my chip select, this green line. I'll wait for it to synchronize again. You can just see tiny little spikes there. So if I can, what I'll do, I'll synchronize it on this and expand the view. Right, this is our chip select. So we bring the chip select low, or frame select. And then this is the SPI, so it generates its own clock when you do an SPI write. So there's 16 clock cycles, and so it's idling low, 16, then a gap, except for these cursors, I can't see the frame select. So frame select on, off, so that's tiny little, I think it's something like a 50 nanosecond spike. So if I bring in the whole lot, right, there we are, frame select, 16 bits, chip select on and off, chip select, chip select, chip select, and then it's off. And it's 16, 16, 16, 16, 16. And you think, why is it not working? That should be spot on. But going back to the data sheet, look here, T8. So from the last clock to the chip select turning off or going high, T8. This is why it wasn't working, or why I understand it wasn't working. So T8 max is T4 take T5 nanoseconds max. So T4 take T5. There's T5, there's a high clock, and T4 is that clock turning off to that clock doing a full cycle. So T4 take T5 is, I think, T4 is 25, T5 is 10, so what did it say? I'm lost. T4 take T5, so T4 25 nanoseconds take T5, so that's 15 nanoseconds. Go back to the scope, expand this out. I figure out this time here for this chip select turning off to the edge of this last clock, or here to here, or here to here, something like 15 nanoseconds, and hopefully you can see that we're on 1 microsecond of division, so that's 1,000 nanoseconds, and I don't call it another 500, so we've got 1,500 nanoseconds, and the limit is 15. So the answer is go to frame select, let the microchip and MikroElektronika's compiler, which is all set up, do the frame select. So if I show you, get the SPI data sheet for microchip, and it tells you about these frame support bits. So that frame support bit enable, bit 1, so frame support is enabled SS, so in my case slave select 3 pin is used as a frame select output. So that's why that pin at the top I chose let D14, that's slave select for SPI3. Forget these bits didn't actually work. I haven't looked at the errata sheet for this chip, but maybe these functions don't work on this chip. This was correct. So frame sync pulse width bit, to synchronize the frame on every clock or every character. So the character is, I'm trying to point at the screen again, the character is 16 bits wide, not 1 clock wide. Then frame pulse, just make sure it's active low, and then this bit here, got it working. Undelete that. Frame synchronization pulse coincides with the first bit of the clock. So this is how you activate the frame select on a Pic32 MX795 using MikroElektronika's software. So depending on what you're using, use the frame select. It's very, very quick, very accurate, and my chip started working. So now if I now delete this chip select, delete, 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 delete. Now program, build and program. Right, let the screen update. Right, so now, because we're on frame select, the clock doesn't turn off. You can see there. And using the code, the frame select coincides with that first clock edge, which is SPI, the frame enable, frame synchronization bit coincides with the first clock. So back to the scope. So each one of these frame select coincides with the first bit of 16 clocks. Now if I run to the end, I've run to the end of the frame. So look, this is the end of the frame, and now that's my 5 bits of written. Now look at the frame select, bang on when that's the last clock of the 16th or the 16th clock. There's no delay there at all. It's probably overlapping. Let me zoom in a bit more. Look at that. So I'm zoomed in 500 nanoseconds, and there is no delay at all. It's actually turning off probably a bit before, but you're allowed to do that. You're allowed to turn off in the middle of a clock. And my analog device started working. You can see no delay. We're on 200 nanoseconds, no delay, and that's it. This, as I say, this analog device started running. And there's another look at the waveform generator running up quickly. We're up at 778 kilohertz. So these lines, because this screen updates at 50,000 times a second, this is actually the data being written. So you lose the data. It takes 7 clock cycles for the program to update. So you don't get a waveform for 7 clock cycles, or 7 clock cycles of the 25 megs. But you can see we're up to 230 kilohertz, and I haven't tested what this goes up to with my code, but the actual spec of the device, 0.1 hertz to 12.5 megs, so half of the clock, which is 25. As I say, that's the data, and on a cheap scope you wouldn't actually see that. And certainly testing an amplifier you wouldn't see that, and an amplifier wouldn't be able to amplify frequencies up at that sort of range, or not audio amplifiers. But you can see it's creeping up slowly. That would go all the way up to 12.5 megs, so 300 kilohertz. Not bad. And another look again. I'm using MikroElektronika's EasyPic Fusion version 7. It comes with a TFT, but I'm not using TFT. I've actually got the backlight on just so I know there's power. I had terrible trouble with the device. I had this on extended leads and it wasn't communicating properly, so I shortened the leads and it's stuck one of the pins in one of these click sockets. But smart. Hopefully this has helped. It's taken me days to understand why a simple chip, simple communication wouldn't work. Had a look at loads of forums, seems loads of other people are struggling, and it seems to be down to that frame select. If the frame select turns off too slowly, the chip won't always update. Hopefully this has helped. Thank you very much.